Okay, so we already, right? Today we'll prove the master theorem. We're going to use this fact, this AMGM-like inequality that I described on the first part of this lecture, and I also convinced you that it's enough to upper bound, and why is it a good reason to upper bound this moment? Okay, so we can now start with the actual proof. So we're going to define just a few objects, right? We're going to want we have x, we want to define x condition on a certain coefficient I, specific coefficient I being positive or being negative. And so we'll define x plus I as x with the conditioning that the epsilon I is positive. So really what is this? This is hi plus the sum for j different than I, epsilon j, hj. And we're going to define x minus I as x condition on epsilon I being negative. Okay, so now we have all the ingredients, we can start. Right, so our goal is to control trace of x to the 2p. Okay, so this is what we'll be trying to do. Now, as we control, trace, right, we want to make the hi show up, so let's rewrite this. Right, this is the same thing, of course. I mean, we're just doing algebra manipulation. Well, x to the 2p minus 1, right? I'm going to start peeling off x's, right? I'm going to use a recurrence relation. Basically, I'm going to recur and make the 2p get smaller and smaller. But now what is this? This is just the sum, right? Let me put expected value here. Expected value of the sum from I from 1 to n of the trace of epsilon I, hi, x to the 2p minus 1. Right? And now this expected value, right? This expected value is with respect to the epsilon I and to respect to the epsilon j's that are not I. Right? So let's rewrite this. Let me go over here. So I get expected value, right? With respect to, say, j, not I. Then I have an expected value with respect to I. Right, of the sum, well, I need to put the sum outside, otherwise there's no I to start with, right? So I have a sum over I from 1 to n. This is just, right, a different way. It's like you have an integral over the distribution. I mean, in this case, they're just sums, right? But it's like an integral distribution of all the epsilons. I'm just integrating first with I and then with the other ones. Okay, so then what do I have? Trace of epsilon I, hi, x to the 2p minus 1. Okay, but now what is this? Now this is easy to write, right? Because you want n expected value with the j not I. And now what is the expected value of this in I, right? It's just half of the, right? It's just the average because epsilon I only has two possible values. It's just the average between when epsilon I is positive and when epsilon I is negative. So what do we have? When epsilon I is positive, we have hi, right, times x plus I 2p minus 1 minus, right, so plus the other term, but it's minus hi x to the 2p minus 1, right, condition on the epsilon I being minus 1, right, so let's write this again, sum from I from 1 to n, expected value taken with j not I. I mean, sometimes I'll remove this term because it'll be clear from context. I'll remove this index, it'll be clear from context. And now what we have is trace of hi, and we have x plus I, 2p minus 1, minus x minus I, 2p minus 1. Okay, so now we're going to use another trick. We're going to write this is a telescopic sum. Okay, well let me maybe first collect this term. So I'm going to take away these definitions. Okay, I think if we're going to use them in a way that it's important to remember exactly what they are, then I'll write them again. But we have that trace of x to the 2p. Expected value is this is equal to, all the half can come outside, half sum from I from 1 to n of expected value, right, of j not I, trace of hi, x plus I, 2p minus 1, minus x minus I 2p minus 1. Okay, and now what we're going to do is we're going to write x plus I 2p minus 1 minus x minus I 2p minus 1 as a telescopic sum. Okay, so the idea will be to write this as a telescopic sum. Okay, I'm going to write the sum, and then it's one of those things that it's easier for you to just take, maybe pause the video, take a minute or two to convince yourself why this is the case. Okay, but the idea is that, of course, when you have a polynomial like something to some x to some power minus y to some power, there is a term inside that's x minus y, right? This is x minus y times something. I mean, one way to see that is that this is 0 when they're the same, so there should be a term like x minus y factoring in. And in matrices, something similar is going to show up, and we're going to make it show up in a telescopic way. So I'll write the expression, and then I think you should pause the video and convince yourself that this is the case. Okay, so this is the telescopic sum. There's no minus here. Right? Now, okay, this is the kind of thing I recommend. Just pause the video and try to convince yourself of this. But it's not so hard to see that basically what you get here is terms like x plus I to some power, either q or q plus 1, and then x minus I to some other power, either 2p minus 2 minus q or 2p minus 2 minus q plus 1. Right? And the terms that have one more minus I term have a minus sign, but as q is increasing, right, or decreasing, then you start getting more of these terms over on this side, and so for a certain q, it will cancel out a term of the q immediately after, right, because you have something like xi to some power, x to the minus I to some other power, and that offset with the minus sign, but since you're summing all of them, they all cancel, right? One term from q equals, say, 1 will cancel with the q equals 2, and with another one of the q equals 0. Right? This is what's known as a telescopic sum, right? When the sums all start canceling out in nearby terms. And so really the only thing that survives is the q equals 0 term, the big power to the q equals 0, which is this one, right? You get minus x minus I times x minus I to the 2p minus 2. And so you get x to the minus I to the 2p minus 1 with the minus sign, and the term of q to the 2p minus 2, the one with the biggest power, which is this one, where you get exactly that. Okay, so this is correct, and I recommend just pause the video and convince yourself of this, and I have this also in the notes. Right, but now, okay, so now this, of course, is just equal to 2hi, right? Because this is the sum, this is this power, this is conditioned to the term the epsilon I being 1. This is conditioned to be minus 1, so when we subtract, we get 2 hi's, right? And so what we have immediately in the top is we have that the expected value of the trace of x to the 2p, right, is now equal to, right, the 2 will cancel to that half, so we have sum of I from 1 to n, expected value of j naught I, trace of, and you'll start seeing that thing showing up, hi, x to the plus I 2p minus 1, right? H to the I, oh, I need to, right, of course, sorry. I want to do this one, so I need another sum, right? I have a sum from q0 to 2p minus 2, and now this, right, I get the trace, right? The trace, I can put it inside the sum or outside the sum. I moved the sum outside of the trace, but nothing really changes. And now what do I have? I have hi times this terms, right? So I get x to the plus I to some power q, right? Then I get hi again, right? The 2 cancel with the half, and I get x to the minus I, 2p minus 2 minus q. Okay, and now I'll try to close everything. Yeah, okay. So now now we can use our AMGM inequality, right? Because now we can use this. Because we're exactly in that setting, right? Where we have a trace, right? Some sum from q0 to r. So now we have to use it with r being q minus 1. With r being p minus 1. Right? Because what we have sum from q equals 0 to p minus 2. Exactly this. Trace of h, which is the hi. The w is now the x plus y to the q. Another h, and this to the 2p minus 2 minus q is exactly what we have there. So using the AMGM inequality, we have that this is smaller or equal than, okay, let's try to not make a mistake. Right from 1 to n, expected value j different than I. And now we have this sum. Right, the sum with this term is smaller or equal than, and we get 2p minus 2 plus 1, so 2p minus 1 over 2 times the trace of hi squared times x to the plus I to the 2p minus 2 plus x minus I. 2p minus 2. Okay. Now, okay, and here is exactly where the loss happened. The loss that I talked about of how the terms should be the biggest when the HIs are together, because we're not using that, we're just bounding essentially every term in this sum by the terms in which they are together, we get this 2p minus 1 factors. But really, the terms on when this and this are both than 0, in some cases they should be smaller, and so you wouldn't get this extra factor. And this factor is going to be what's going to create this logarithmic factor in the end, as we'll see. Okay, but let's see if we can simplify this more. So now, okay, so we have the expectation here with respect to j not I, but here we really have an expectation with respect to I, right? Because this is exactly the expected value with respect to I of x to the 2p minus 2, maybe twice that. Right? Because what's this expected value? Well, it's x plus I to the 2p minus 2 plus x minus I, because, right, you just get plus or minus 1. The expected value will be conditioned on being plus 1. Average that is conditioned on being minus 1. So this 2 will cancel with that a half, and we get something which is exactly, right, this will be equal to the sum from I from 1 to n. Now this expected value over I can come all the way outside and transforms this into a proper expectation over everything. Right, so expectation over everything. Now we get a 2p minus 1, right, because this 2 cancel that 2, and we get trace of hi squared times x to the 2p minus 2, right? Remember that nothing else depends on epsilon I in here, so this expectation can come all the way outside. Okay, so now let me erase and put it all the way over there. Okay, now we have a very nice inequality. Right. We have that this is smaller or equal than. We have sum, I mean the 2p minus 1 can come outside. Right, and now what do we have? We have the sum from I from 1 to n, expected value of, and the expected value of the sum I can put them in whatever order, trace of hi squared times x to the 2p minus 2. Right, so you see here I've already impaled 2 x's out of this power. Right, now let me write this in a bit of a more suggestive way. Oh, let me move the sum inside. So what do I have? I have that, right? I take that, so let's see, expected value of the trace. I'm moving the sum inside because the sum only matters for this one. Okay, but now I have the trace of the product of two matrices, they're positive semi-definite. So for sure this is smaller or equal than if I take this out in its spectral norm. So I have 2p minus 1. Right, and now I have, right, I can take this out in its spectral norm. Since this is deterministic, I can even take it outside of the expectation. So I have spectral norm of times the expected value of the trace of x to the 2p minus 2. Okay, but now we're basically done, right? Because now I have a recurrence relationship. Now all the hard work is done. Right, because now what do we have? We have that this is 2p minus 1 sigma square expected value of trace x to the 2p minus 2. So now I can just do this over and over again. Right? I can just do this recurrence over and over again. And so what do I get if I do this over and over again? I get that, right? I keep doing this. So now do this, do this. Right, over and over again. Okay, so I do it until I get x to the 0. So what do I get? Okay, let's keep track of all the terms. So I go to 2p minus 2, 2p minus 4, all the way to 0. So I'm going to get 2p minus 1 times 2p minus 3, all the way, right, until I subtract, until I go to 2p minus 2p here, so 2p minus 1 here, so I get a 1. Right, so I have all these terms. Sigma gets multiplied p times, sigma squared shows up p times. Okay, so maybe let's, so I have sigma to the 2p, right? This has a name, by the way, this is 2p minus 1 double factorial. Right, the factorial would be if I take 2p minus 1 times 2p minus 2 times 2p minus 3 and so on. Here I just get every other term, this is the definition of the double factorial. And then the term that survives is the expected value of trace of x to the 0. But x to the 0 is just an identity, right? And so trace of x to the 0, well, it's now deterministic, so the expectation doesn't do anything. This is equal to d, right? Because it's a d by d matrix. So what we get is that the expected value of the trace of x to the 2p is smaller or equal than 2p minus 1 double factorial, sigma to the 2p times d. But really, we want this to the 1 over 2p, so let's collect those terms. This is smaller or equal than, and we have 2p minus 1 double factorial to the 1 over 2p. Right? But now what is this term? Well, if I was multiplying, I didn't make them smaller, I just kept being 2p minus 1 over and over again. We would basically get p over 2 of such terms. Or p of such terms, sorry, right? We have p factors. If the roll of size 2p minus 1, we would get p many terms. But now we take that, so we would get this to the p, but we're dividing, we're taking to the power 1 over 2p, so we expect something like square root of this. And in fact, this is almost correct, right? It's a little smaller than that. But this will be roughly a square root p factor, and since p is going to be a logarithmic factor, then we'll explain the square root of logarithm. Now I get what? Sigma to the 2p, with 1 over 2p, I get sigma times d to the 1 over 2p. Right? And because this is roughly, right, because this is roughly square root p, right, this looks a bit, well, I'll do it with proper constants in a second, but this looks a bit like square root p, sigma, d to the 1 over 2p. But if I want to make the d disappear, then I need to take p to be something like a logarithm, right? Because what is this term? This term is exponential of, right, 1 over 2p log of d. So if I want to make, if I want to make the dimensional factor disappear, I need to make the p cancel out the log d, so the p needs to be something like log d, but then I pick up a square root log d factor. And this is exactly where that, is exactly where this term is coming from. That is precisely from there. Now to do this with, proper constants, then it's not so hard to see. This basically uses Stirling. I mean, I put a reference in the notes, but this is just the use of use of Stirling and some simple algebraic manipulations. But it's not so hard to see that you have that 2p minus 1 double factorial is smaller or equal than right? I mean, this is exactly the intuition I gave, that you should get something like 2p plus 1, or 2p minus 1 in that case. I mean, this is just so that it for sure is bigger. Then you should get something like 2p minus 1 to the p. The Stirling gives you an improvement of e. Right, and so now all you have to do, right now all you have to do to get to this inequality here is to take p to be the ceiling of log d. Right, and if you now make p be the ceiling of log d, then use this fact and work out an upper bound for this, right? It's just you have everything here, right? You have d to some log d, some 1 over log d, so all that cancels out. This will get some 2 times, right? The 2 times the ceiling of log d, which is exactly the kind of thing that shows up here, right? And so if you plug in this value, you now get exactly this inequality with the right constant, right? So this is now proved. Now, the thing that I want to bring the attention to here is that where this logarithmic factor came from, right? This logarithmic factor came from the fact that when we're bounding, we bounded everything by the terms that we believe were the biggest, right? Every term was bounded by the ones where the HI showed up together. But if potentially those are way bigger than the other ones, then we wouldn't pick up this 2p factor in front, right? There would only be 2 terms of this size, and the other ones would potentially have much smaller size. And if that was the case, then this p here would never show up, and we would never get the square root log. And so the hope is that if the terms are the smaller one can improve over this inequality. And indeed, there's a paper that does a slight improvement over this, and the references are in the notes, where you basically bound other terms by something a little smaller. It's not yet quite the final answer, but it does do something. And more importantly, it shows that this avenue of trying to control better these middle terms is potentially fruitful. Okay, so in the next lecture, we'll move on we're done with matrix concentration, and we'll move on to other things, including approximation algorithms, max cut, and so on. All right, thank you.